Welcome to this lecture series in real analysis. In this lecture, we'll continue our discussion on convergent sequences and look at a special type of convergent sequence. And let us recall what we need. So, of course, we will need the notion of a convergent sequence. So, a sequence xn in R is said to converge to a point x, to a real number x, if this happens, which is for all epsilon greater than 0, the distance between xn and x is less than epsilon, ultimately. Right? We saw the kind of the meaning of it. You have this point x on the real line. Then whenever you choose a room around x, you find that ultimately, after certain point of time, all the points of the sequence are inside this room. And this does not depend on the choice of the width of the room. You may choose smaller and smaller rooms and still find this to be true. And that is what is meant by convergence. Okay, this is a notation to just indicate that xn converges to x. This is another notation. So maybe I'll separate them. So this is one way to express, this is another way to express. This is also one way to express. This is a lazier version of the previous one because here it's kind of improper to write it this way. Similarly, this is the lazier version of the previous one. Sometimes we may be a little less lazy but still pretty lazy and write things this way. However, these lazy notations don't generally cause any confusion. If you feel confused by them, use the fuller versions. Okay. Finally, once we have the definition of convergence to a point, we can now define a convergent sequence, which we did in the previous lecture. So we say that this is convergent if there is some point on the real line such that xn converges to it. Okay, so first we define convergence to a point, right? When do we say that this converges to a point? We defined it, and then we define a sequence which is convergent by declaring it. We declare a sequence to be convergent if there is a point to which it converges. Also, the point to which a sequence converges is called the limit of the sequence. We saw that this is unique. A sequence cannot converge to two different points. Okay, let's also recall the notion of a bounded sequence. A sequence xn in R is said to be bounded if there is a positive real such that the absolute value of every element in the sequence is controlled by this positive real. So that's a very simple definition. And with that, let us continue. Here are some problems for practice. And now let us move on. Okay, so what is a null sequence? This is the central concept of this lecture, and it is going to be a very short lecture. So a sequence xn in R is said to be a null sequence if it converges to 0. So it's first of all a convergent sequence and its limit is 0. That is what a null sequence is. So not much to say about it. Here is an example of a null sequence. If you define xn as 1 by n for each natural number n, then this turns out to be a null sequence. We saw the proof of this in the previous lecture, so let me not repeat it. And let us move on. So one can recast the notion of convergence in general to null sequences. It's kind of a childish thing, or it may seem like a childish thing, but such reductions are very useful and we will find use for them in subsequent lectures. So fix a real sequence and an element x in R. Then the following two statements are equivalent. The first is that xn converges to x, The second is that this sequence converges to 0, meaning it is a null sequence. So if it is not clear about what is meant by this is the sequence whose nth term is this number, the difference between xn and x. So that's what this guy is. Okay. All right. So it's a straightforward proof. Let me do one direction. So we will do the proof of 1 implies 2, and the reverse would be left as an exercise. Okay. So what we are given? We are given that we are given 1, that is, this is the case. I'm kind of just restating things. And we will refer to this as star. Of course, I could have just said that this is 1, but anyway, let's refer to this as star. Okay, and define yn as xn minus x for all n. And now the problem is to show that, this thing is a null sequence. This is exactly what the statement of this guy is, that this sequence is a null sequence. Okay, but just let's unravel this. So that is, we want to show that that is, yn converges to 0 as n approaches infinity. So this is just a way to read it out. I mean, it means exactly that yn converges to 0, but when we write this, we read it as yn approaches 0 as n approaches infinity. That is one way to read it. Okay, which is to say that for all epsilon greater than 0, this happens ultimately. We just unravel the meaning of this. That's what this means. Okay, so this is what we will show. But now, by star, we have for all epsilon greater than 0, this happens. This is exactly what star is. This is equivalent to star. This is the meaning of star. But what does this mean? Just a change of notation tells us this is the case. And this is what we wanted. This is what we wanted to establish, and we are done. So it's a very, very simple proof. Of course, the reverse direction is remaining, but that can be done by reversing these steps. All right, so it's a very simple reformulation of convergence to a point x. You just say that this guy is a null sequence. Okay. Now for another unrelated lemma, and this will be the last thing for this lecture. So fix a null sequence and fix a bounded sequence Bn. Then this sequence is also a null sequence. So again, what is this sequence? This sequence is the sequence whose nth term is the product of the nth term of this sequence and the nth term of that sequence. All right. So yeah, this is also a very easy proof, but let's do it in full detail. So again, what we are given is this is 0, right? We are given that this is the null sequence, which means this. So let's box it, call it star. All right. Now, since this guy is a bounded sequence, we have, or there exists, a positive real capital K such that this is true for all n, right? Immediately from the definition of a bounded sequence. And now define yn as the product of xn and bn for all n, of course. And we want to show that yn is a null sequence, which is to say that for all epsilon greater than 0, this happens ultimately. So this is our goal. This orange thing is our goal. To prove it, fix an epsilon, and we will end up showing this part. Once we do this, we will be done. All right, so now by star, we know that for all delta greater than 0, this is the case. Right? This is exactly the meaning of star. We are not using the symbol epsilon here. Instead of epsilon, we have used delta, because if we use epsilon, it would be improper. We have already reserved epsilon for another purpose. So we don't want to, or we cannot reuse it again and write a confusing proof. It's illegitimate to use it again here. All right. So we have the statement, and now this in particular means that this happens ultimately. Now what did we do? This statement is true for all delta. This statement is true for all delta. So we can choose a specific value of delta, one of our liking, one which is suitable to our needs. And this is the value that we choose. Now it may seem a bit contrived as to what prompts this, but you will see what prompts this in the next step. So this implies ultimately, right? If this is true, then obviously this is true. We just multiplied both sides by that thing. But now this is at most capital K. So this implies this product, which I am writing this way, because this is how absolute values behave, this is less than epsilon by K times K, ultimately. Now why is this? All we did was, this is at most K. This is all we did. And this cancels out to give us xn times bn is yn, and the right hand side is epsilon, and this happens ultimately. And that's it. That proves what we wanted to prove. We wanted to establish this, and we have done that. So this finishes the proof of this theorem, if you will. Alright, so this is all for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.